Good morning, sir.
Good morning. Good morning.
5 minutes, sir. We will start.
Okay.
Sir, 5 minutes, sir. Will start.
Okay.
எடுக்கிறீங்களா?
YouTube ಅಲ್ಲೇ open ಮಾಡಿ.
ಗೋರೇಗೌಡ ನಮಸ್ಕಾರ.
ನಮಸ್ತೆ ಸರ್, ನಮಸ್ತೆ.
ಲೇಟ್ ಆಯ್ತು.
ಇಲ್ಲ
ಸ್ಟಾರ್ಟ್ ಮಾಡೋಣ. ಓಕೆ. ಗೊತ್ತಾಯ್ತು ನನಗೆ, ಅದೆಲ್ಲ ಗೊತ್ತಿದೆ. ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. It is a pleasure to welcome all the participants and dignitaries to this webinar. Before that, I would like to share a few words about the Department of Mathematics. The Department of Mathematics is functioning right from the inception of the college in 1964. And we have different courses like BSc with 3 majors. Now, of course, under national education policy, we may opt for 2 major systems like that. And we have BCA and even vocational courses, BVoc. For all these courses, we teach mathematics. In the year 2012, we started with MSc in mathematics. Now, the department has been recognized by the University of Mysore as a research center. So students, once they join for undergraduate course here, if they are interested, they can pursue the postgraduate program also. And afterwards, if they have eligibility, they can do the research work in the Department of Mathematics, JSS College. The Department of Mathematics has two math labs. Two math labs we have, and we are organizing national and international conferences regularly. Just for because of COVID-19, we could not arrange any programs during this period, but this time we have organized a webinar just to make the young minds to know something about real numbers, because all of us we are familiar with numbers, number system, real numbers, rational numbers, like that. Is it okay? Okay, right. But if you ask any student, even young teachers, they may not be able to define what a real number is, what an infinite set is, what is countability, what are countable sets and uncountable sets, like that. They may find it a little bit difficult. So keeping that in mind, I thought of organizing a seminar, that is online seminar, we call it as webinar, by inviting an eminent personality, an young, we can call him a mathematician, Dr. Boregowda. So he is the resource person for this program. Dr. Boregowda at present is working as professor of mathematics in the Department of Studies and Research in Tumkur University. He has he did his post-graduation from Coimbatore University with first rank and 5 gold medals. And he has the credit of completing that a NET program, NET, any National Eligibility Test program, in a row for 3 times. And he did his PhD program from, and he did his PhD under the guidance of Dr. Chelaviraju from Tumkur University. The subject on which he submitted his thesis was chemical graph theory. And he has, to his credit, has 25 international publications. That too, in the journal published in the journals, reviewed by peer-reviewed journals, international publications. And also he is guiding for NET and JEE students also. And he is an active man and always doing one or the other thing to encourage talent, young minds. So it is really a great pleasure to welcome Professor Boregowda to this program.
Thank you, sir. Thank you.
Now, I welcome all the participants, maybe teachers who are teaching in different colleges, and even students from Mysore University or other universities in Karnataka and even Tamil Nadu and other states. I hope that you will enjoy this program and appreciate this, because this is the basic thing that one has to know. You have studied mathematics at one stage, means you should know what a real number system. Is it a field? Is it a vector space? Is it ordered field? Why is, if a field of real numbers is ordered, why is the field of complex numbers is not ordered? You should know all these things. My sincere request is just apply your mind, concentrate on this and try to understand this one. Definitely you will enjoy, because resource person is such a man, and you will be knowing. No need to explain, no need to once again say anything about him. So I once again welcome all the participants to actively participate in this program. And one thing, Chief Executive Professor Sambashivaya and Principal Vannappa, both are busy with some meetings, therefore they cannot attend to this program. I welcome even those two also for this webinar. Now I request Dr. Boregowda to continue with his lecture. Over to Boregowda. Please, Boregowda, you can.
Yes, sir. Yes, sir. Sir, break another idea, Madhya.
ಏನಿಲ್ಲ ನಥಿಂಗ್ ಲೈಕ್ ದಟ್ ನೀವು
Nothing
ಬೇಕು
like-
ತಗೊಳ್ಬಹುದು.
Okay. Like just okay.
Yes, ತಮಗೇನಿಲ್ಲ. If you want to
Okay.
can.
Okay. Thank you, sir, for your nice introduction.
ನಾನು ಬರ್ಬೋದಾ?
At the outset, I would like to thank all administrative personalities and especially Professor Ningana sir for having invited me as a resource person to this webinar on real number system and counting of sets. Since I am told more than 70 to 80% of the participants in this webinar are going to be BSc students and MSc students, I would like to stick my lecture to the basics of counting numbers, counting of sets, as well as real number system. That's why I wanted to teach these two things in a classroom like environment. That's why initially I thought of preparing slides, PPT, and sharing the PPT, and I thought of explaining the things using PPT. But after having come to know that most of the aspirants are from BSc and graduation and undergraduation, I decided to have a classroom like interaction, that is writing and discussing the things and sharing the things in both the way. So that's why I'm going to share my iPad to you people. Please bear with me for 2 minutes. Title of my lecture, today's lecture, is Counting of Sets and Real Number System. So in the first half of my lecture, I'm going to share some knowledge which I have been teaching to the young minds over a period of last 15 years on counting of sets. And in the second half, I will switch over to real number system and what are the properties that a real number system is going to exhibit, and what is meant by an ordered field, what is meant by a complete ordered field, whether R is going to be complete or not, whether Q is going to be complete or not, and what is order completeness axiom, that is least upper bound axiom of real numbers. And finally, I'm going to discuss some of the applications of order completeness axiom of real numbers, that is Archimedean property and allied results. This is what the structure of my today's lecture. So in the first session, that is first half, I'm going to discuss what is meant by counting of sets. What is the difference between countable sets and uncountable sets, and some results regarding countability and uncountability of sets with few examples. Before starting with counting of sets, just I would like to rebrush the basics which are essential to understand the difference between countability and uncountability of sets. I think being a student of maths, BSc or MSc, you must have gone through the definition of function and types of functions. So in types of functions, I think you might have come across, I think all of you are aware of injective functions or one-one functions. Injective functions or one-one functions. A function f from a to b is said to be injective, as we all know, if different elements of a have different images in b. If different elements of a have different images in b. Different images in b. If at least one pair of elements of a have distinct elements of a, if at least one pair of distinct elements of a have same image in b, then such a function is not going to be injective or one-one. I think all of you are aware of this definition, very fundamental definition of injective function or one-one function. Graphically, if f is a function from R to R or a subset of real line to real line, an injectivity is verified by drawing a horizontal line test. That is, if f is a function from R to R or a subset of real line to real line, if we plot the graph of the function in the Cartesian plane, anywhere in the region on y-axis, if I draw a line parallel to x-axis, anywhere in the region of domain, if I draw a line parallel to x-axis, either this line which has been drawn parallel to x-axis has to meet my graph at exactly one point, or it should not meet the graph at any point. This is what is geometrical meaning of or graphical meaning of one-one function or injectivity of functions. For example, if I consider if f is a mapping from R to R defined by f of x is equal to say simple x, f of x is equal to x, clearly it is nothing but a straight line passing through the origin making an angle of 45 degrees with the positive direction of x-axis. So anywhere on y-axis, if I draw a line parallel to x-axis, our line which has been drawn parallel to x-axis is meeting my graph at exactly one point. Hence, f is going to be 1, 1. The meaning of this geometrical orientation is different elements of the domain are going to have different images in the code. That is what is the meaning of 1, 1. If I take one more example like f from R to R defined by f of x is equal to mod x, and if I plot the graph of this mod x function, this is going to be the graph of this mod x function, as all of you are aware of this thing. But if I draw a line parallel to x-axis, at some point it is not meeting my graph, meeting our graph at any point, but at some point it is meeting the graph at more than one point. This is the case of non-injectivity or not a one-one function. Not a one-one function. Because if I draw a line parallel to x-axis which is passing parallel to y-axis, parallel to x-axis, and at this point, if say at 0, 1 or 0, 2, if the line drawn parallel to x-axis, then the line drawn parallel to x-axis is meeting our graph at more than one point. So that means there are two different elements in the domain, because domain is always measured along x-axis. Domain is always measured along x-axis. Domain is taken as R. So at x is equal to say a and x is equal to minus a, the height of the graph is same. That means both x is equal to minus a and x is equal to a are going to have the same image. That is, suppose y1. This is y1. This is also is at the same height. That means, but x is equal to minus a and x is equal to a are different elements of the domain, but their images are same in the code. Hence, f is not going to be 1, 1. So geometrically or graphically, when we plot the graph of the function, a real function, especially a real function, particularly, and if I draw a line parallel to x-axis, anywhere on the y-axis, either the line should not meet the graph at any point, or if it meets the graph at any point, it has to meet the graph at exactly one point. It should not meet the graph at more than one point. If at any point on y-axis, if any line drawn parallel to x-axis is meeting your graph at more than one point, that is the case of non-injectivity. That is the case of non-injectivity. It means the function is not 1, 1. It is going to be many 1. It is going to be many 1. So this is graphical meaning of 1, 1 or injectivity. Algebraically or analytically, how to prove 1, 1ness of the given function? Analytically, how to prove injectivity of the given function? Suppose if f is a function from A, a subset of R to R, is any real function or any function, then to prove f is 1, 1 or not, we have to assume f of x1 is equal to f of x2 for any x1, x2 belongs to R. Suppose f of x1 is equal to f of x2 for any two members x1, x2 belongs to the domain A, a subset of R. By using your mathematical or using the definition of the function that is supplied to you, you have to prove that x1 is equal to x2 by using the known mathematical properties. F of x1 is equal to f of x2, that is the assumption you have to make in the beginning, and you have to make use of the rule defined by f in the place of f of x1 and f of x2, and using some mathematical manipulations, you are supposed to finally prove that x1 is equal to x. If you can prove this one by assuming f of x1 is equal to f of x2, if you can prove that x1 is equal to x2 through your mathematical manipulations or mathematical knowledge, then we can conclude that f is going to be 1. Or else you can also assume that f of x1 is not equal to f of x2 for any two x1, x2 belongs to the domain A. And by using your mathematical knowledge, if you can show that x1 is not equal to x2, that would also mean that f is not going to be 1. This is the analytical method of showing a given function is 1, 1. But graphically, 1, 1ness is when you draw a line parallel to x-axis anywhere on y-axis, the line drawn parallel to x-axis either has to meet your graph at no point. If it meets your graph at any point, it has to be the unique point. If it is meeting your graph at more than one point, then the function is not going to be 1, 1. That's what is the meaning of 1, 1 function. But if f is a function from A to B, necessarily cardinality of A should be less than or equal to cardinality of B. Therefore, the necessary condition for 1, 1 function, necessary condition for a function f from A to B to be 1, 1. To be 1, 1. A necessary condition for a function f from A to B to be 1, 1 is cardinality of A is less than or equal to cardinality of B. Means cardinality of the domain should be less than or equal to cardinality of the codomain. This is the necessary condition for any function to be 1, 1. Not sufficient. Just because of the fact that cardinality of the domain is less than or equal to cardinality of the codomain, it doesn't mean that f is going to be 1. But if f is a 1, 1 function from S at A to S at B, 100% cardinality of A should be less than or equal to cardinality of B. This is necessary condition. Very important property. You must remember this one in order to identify the difference between countability of sets and uncountability of sets. A necessary condition for the existence of 1, 1ness between A to B is cardinality of the domain should be less than or equal to cardinality of the codomain. It is necessary but not sufficient. Similarly, let me go for surjective function. Just I'm brushing up the things because these things are very essential to define similarity of sets. Once similarity of sets concept is clear, you can easily identify what would be the difference between countability of sets and uncountability of sets. Surjective function. Surjective functions. A function f from A to B. A function f from A to B is said to be onto. Is said to be onto, as we all know, or surjective, is said to be onto or surjective if f of A is equal to B. That means, that is, if range of f is equal to codomain. If range of f is equal to codomain, then f is going to be onto or surjective. In other words, if every element of codomain has at least one preimage in the domain, then such a function is going to be onto function. Because for a function, it is necessary that every element of domain should have a unique image in codomain, but it is not necessary that every element of B should have at least one pre-image. It is not necessary for a function. But for an onto function, it is necessary that every element of codomain should have at least one pre-image in the domain. Suppose this is the domain and this is the codomain. If f is a function defined from A to B, each and every element of domain should have unique image in codomain. Each and every element of domain should have unique image in codomain. But it doesn't mean that every element of codomain should have at least one pre-image in domain. If x, suppose if x is connected to y, then y is called image of x and x is called pre-image of y. Y is called image of x under f and x is called pre-image of y under f. For f to be a function, f has to satisfy two conditions. That is, each and every element of A should be connected to a unique element of B. That means each and every element of A should have a unique image in B. But it is not necessary that all elements of B should have a particular element of B should have an pre-image in A. Suppose if I take like this, just 1, 2, 3, 4, 2 elements here. If I define like this, so it is going to be a function because it is satisfying both the requirements of a function. What? Every element of domain should have a unique image. For A, B, C, D, this element X is going to be the unique image. But Y has no pre-image, but X has 4 pre-images, but Y has no pre-image. So for f to be a function from A to B, it is necessary that all elements of domain should have images in B such that every element should have unique image in B. But it is not necessary that every element of codomain should have at least one pre-image in domain. But for a function to be onto, it is in addition to be a function, it has to be onto. Function plus ontoness. Function means every element of domain should have unique image in B. But ontoness requires every element of codomain should have at least one pre-image in A. So combining both the concept of function and ontoness, we can state the definition of surjective function like this. That means a function f from A to B is said to be onto or surjective if and only if each and every element of codomain should have at least one pre-image in domain. Here, range of f is going to be x only because range is nothing but collection of all those elements in codomain which have pre-images in domain. Range is the collection of those elements in codomain which have pre-images in domain. Here x is the only element in codomain which has pre-images. Y doesn't have any pre-image. Therefore, range of f is nothing but x only. But here range is not equal to codomain because codomain consists of two members x and y, but range consists of only one member, that is x. Therefore, range is not equal to codomain. But ontoness means range should be equal to codomain. It has to be a function first and then range should be equal to codomain. When does range is going to be equal to codomain? If all elements of codomain have at least one pre-image in domain. If each and every element of codomain has at least one pre-image in domain, then range is going to be equal to codomain. That is what is ontoness. Geometrically or graphically, how to check ontoness of the given function, especially real function. Let f from A subset of R to B or be a real function because we are going to have geometrical representation only for real function. Let f from A subset of R to R be a real function. Plot the graph of the function in the Cartesian plane. Look at the region of codomain. Look at the region of codomain. Look at the region of codomain. Means or extent of codomain along y-axis. Look at the extent of codomain along x-axis. So to check ontoness of the given function graphically, you have to look at what is the extent of codomain, because while drawing the graph of the real function, we know that domain is measured along x-axis or taken along x-axis, codomain is taken along y-axis. Here domain, so for the sake of convenience, I take R only, codomain R only. So that means domain is the entire real axis, real axis, that is x-axis, and codomain is entire y-axis in this particular example. To verify whether this function is going to be onto or not, or surjective or not graphically, what you are supposed to do is, by looking at the extent of codomain, anywhere in the region of your codomain, because codomain is always measured along y-axis, anywhere in the region of codomain, if you draw a line parallel to x-axis, that line has to meet our graph at least one point. This condition should happen at each and every point of codomain. If I draw a line parallel to x-axis, that line has to meet our graph at minimum 1 point. Even this property fails at one point of codomain, means if at one point of codomain, that is on y-axis, at any point, if I draw a line parallel to x-axis, if it is not meeting my graph at any point, then function is not going to be onto or subjective. This is what is the graphical meaning of ontoness. Please note this point. In the region of codomain, that's why when you are verifying the graphical meaning of ontoness graphically, look at the extent of codomain along y-axis. If the codomain is R, entire y-axis is going to be your extent of codomain. If the codomain is R plus, only 0 to infinity, means positive y-axis is going to be the extent of codomain. If it is just 0, 1, then just 0, 1, this is going to be the extent of codomain. This is going to be the extent of codomain. If it is minus 1, 1, if the codomain is 1, 1, then this is going to be minus 1 and plus 1. This is the extent of codomain. Only you are supposed to draw the line parallel to x-axis within the region of codomain. You should not draw the line parallel to x-axis outside the region of codomain to check the ontoness or subjectivity of the given function f. Please note this point, yes. Therefore, you are supposed to draw the line parallel to x-axis in the region of codomain only. Anywhere in the region of codomain, but not outside the region of codomain. But if you draw the line parallel to x-axis anywhere in the region of codomain, that line has to meet your graph at minimum 1 point. Even at 1 point of codomain, if you draw a line parallel to x-axis, if it does not meet your graph at any point, then that is not going to be an onto function. For example, let f from R to R be given by, f of x is equal to x square. Simple example, let us take for all x belongs to R. This is the function. This is nothing but parabola. This is the graphical representation of this function, real function f of x is equal to x square. What is the region of codomain? What is your R? R is nothing but minus infinity to infinity, means entire y-axis. Entire y-axis is your region of codomain. Entire y-axis is your region of codomain. Now, to verify whether it is going to be onto or not, you are supposed to draw a line parallel to x-axis at each and every point on y-axis. Anywhere on y-axis, if you draw a line parallel to x-axis, that line has to meet your graph at minimum 1 point for ontoness. See, if I take any point on positive y-axis, and if I draw a line parallel to x-axis at those points, if I take any point on positive y-axis, and if I draw a line parallel to x-axis, clearly all these lines, wherever I draw on positive y-axis, are meeting our graph at minimum 1 point. Hence, function is going to be onto in this region. But my codomain is entire y-axis. I am supposed to draw a line parallel to x-axis at each and every point of my codomain region. This is also a part of my codomain. But if I choose any point here on the negative y-axis, if I draw a line parallel to x-axis, it is not meeting my graph at any point on it. So that means that is the meaning of the meaning of this situation is negative real numbers do not have pre-images. Positive real numbers and including 0 have pre-images under this function f. The meaning, the meaning of this geometrical interpretation is negative real numbers do not have any pre-image, because in the region of negative real numbers, if I draw a line parallel to x-axis, that line is not meeting my graph at any point. That means negative real numbers do not have any pre-image. But if I draw a line parallel to x-axis at 0 on y-axis, as well as at any positive real number on y-axis, the graph is meeting at exactly 2 points at each and every point on positive y-axis, including 0. So that means each and every positive real number is going to have 2 pre-images, because each line is meeting our graph at 2 points, exactly 2 points. That means each positive real number is going to have 2 pre-images under this function. But x is equal to 0 of the codomain. X is equal to 0 of the codomain has only 1 pre-image, because it's meeting my graph. The line drawn parallel to x-axis passing through the origin is meeting my graph at minimum at exactly 1 point. Therefore, the pre-image of 0 of codomain is only 1. But pre-images of each and every positive real number on the codomain are 2, because every positive real number of the codomain are going to have 2 pre-images. But negative real numbers on the codomain do not have pre-images. So that means this function is not going to be undo. But instead of the same function, what I am going to do is I'm going to change the codomain. I'm going to change the codomain. I'm going to change the codomain like this. That is R plus union 0. R plus union 0. Now my codomain has been changed. R plus union 0. That means 0 to infinity on y-axis, including 0 up to infinity on positive y-axis. This is my region of codomain. Now I am not supposed to draw any line parallel to x-axis outside the region of codomain. I should not draw for verifying ontoness of the given function. You are supposed to draw only the line parallel to x-axis anywhere in your region of codomain, not outside the region of your codomain. So here, now we are not supposed to draw these lines because our codomain is restricted to only 0 to infinity. Clearly, that is 0 to infinity. Now, in this region, that is in this region, including 0, anywhere if I draw a line parallel to x-axis, those lines are meeting my graph at exactly 2 points. Means all these positive real numbers, including 0, have at least one pre-images in that domain. Now this function is going to be onto. See, f from R to R defined by f of x is equal to x square is not onto, because negative real numbers do not have pre-image. But f from R to R plus union 0 or 0 to infinity is going to be defined by same rule, that is x square is going to be onto. This is not. This is the graphical meaning of ontoness. Analytically, how do we prove it is good? A given function is onto? Analytically, how to prove a given function is onto? Suppose the given function is a function from A to A subset of R to B subset of, because I am restricting myself to only real functions because we are dealing with real number system and polynomials. That's the aspect. So to prove f is onto, what I am supposed to prove is every element of codomain should have at least one pre-image domain. So for that, let us choose an arbitrary element of codomain. Be arbitrary. Arbitrary means any representative element of codomain. Let y belongs to B, that is codomain, be arbitrary. What I am supposed to do is, if for this arbitrary element of codomain, if I find at least one pre-image in domain, then that would mean that y is going to have at least one pre-image. But y is arbitrary, then that would mean that every element of codomain has at least one pre-image in domain. Because that is a technique in maths. Because we don't know what is the cardinality of the set. If the cardinality of the set is finite, we can easily manually we can verify whether each and every element of codomain has at least one pre-image in domain or not. But when the codomain is an infinite set, by choosing each and every element and verifying whether it is going to have a unique pre-image, whether it is going to have at least one pre-image in the domain or not, it's a highly risky process. The idea is choosing an arbitrary element of codomain. If I can find at least one pre-image for that arbitrary element of codomain in domain, then I can conclude that, or we can conclude that every element of codomain is going to have at least one pre-image in domain. That is the concept of taking arbitrary element. That is one of the technique of method of proof in our mathematical proofing, proofs and disproofs. So logic, mathematical logic, you might have studied these things. Let y belongs to B, that is codomain, be arbitrary. We don't know what is the pre-image of y in domain. For the convenience, for the time being, let us choose some element, say x, as a pre-image of this element y. Such an x may exist, may not exist, I don't know. But for the time being, let us assume some point or some member, say x, be the pre-image of this chosen arbitrary element of codomain as its pre-image. So let x be the pre-image of, let x be the pre-image of y under f. If x is the pre-image of y under f, then by definition of function, we know that f of x is equal to y. Because if x is the pre-image of y, then y is the image of x under f. Then we can express this relation by a notation, f of x is equal to y. Now, to whom we are searching for? We are searching for this fellow x. I don't know whether such a person or such a member exists or not. If exists, whether he belongs to the domain or not, that also we don't know. Yeah, all what we want is, we want to find a fellow or a person for this chosen arbitrary element y, so that that person x should exist in domain and should obey the rule f of x is equal to y, should satisfy the rule f of x is equal to y. Then we can conclude that that fellow x is going to be the required pre-image for this chosen arbitrary element y belongs to code. Now, whom we are searching for? We are searching for this x. So from this relation, simplify for x. Simplify for x. So once we simplify for x, we can express this in the form of x is equal to g of. Now I want to check two confirmatory tests on this fellow x. Some x we have obtained using the relation f of x is equal to y. Just because of the fact that we have successfully obtained the value of x from f of x is equal to y, we cannot conclude that x is going to be the required pre-image for y. We have to apply two confirmatory tests, whether this x exists for each and every y or not. Means whatever the value that y is going to take in code domain, corresponding to that y value, whether such an x exists or not. For that, what you need to do is you have to verify if I give any value for y from the code domain, this g of y is going to be well-defined or not. That means g of y should not take 0 by 0 form or any indeterminate form, or it should not become infinity. For any value of y taken out from the code domain. If for every value of y, if g of y is well-defined, means if it is going to be some finite real number, then x is said to be a well-defined. X is said to be well-defined. Means for every value of y, x exists. That is what does that mean. Just existence of x is not sufficient. Whether that x is in domain or not, that has to be verified as well. That is the second requirement. So what you should do is check x is well-defined. X is well-defined for all values of codomain or not. Check x for x is well-defined or not for all y belongs to b. Even for a single value of y belongs to b, if x is not well-defined, means g of y is not well-defined, then for that value of y, there is no pre-image. Then that would mean that function is not going to be onto or subjective. This is what is the meaning of x is well-defined for each. It should be well-defined for each and every value of codomain. That is the first requirement. Second requirement is for every value of y belongs to b, whether x belongs to domain A or not. That you have to verify. Most of the times this is automatic because you are going to derive x value from this relation f of x is equal to y only. So therefore, most of the occasions, the second condition will be obvious, no need to verify. But first condition has to be verified thoroughly, whether for every value of the codomain x is equal to g of y exists or not. This is what is the analytic. Then if such x exists and is belonging to the domain A, then that would mean that x is the pre-image of y. X is the pre-image of y under F. If such an x exists and if such an x belongs to A, for every y belongs to B, then that would mean that x is the pre-image of y under F, and hence F is onto. So this is the analytical method of verifying whether the given function is onto or not. So let us not go into the details of these things, because we want to go for countability and uncountability. That's why just I am brushing up the things, because unless and until you know what is one-to-ness and one-one-ness of the given function, real function, you cannot understand similarity of sets. Now, what is the necessary condition for onto-ness of the given function? Necessary condition. For onto-ness of the function f from A to B, each and every element of B should have at least one pre-image in A. So that means if B has say m number of elements, A should have at least m number of elements. A should have at least m elements, because each and every element should have at least one pre-image. So if B has m image, certainly A should have at least m elements for function to be onto. So the necessary condition is cardinality of A should be greater than or equal to cardinality of B. This is the necessary condition for a function to be onto from A to B. Not sufficient. Just because of the fact that cardinality of domain is greater than or equal to cardinality of the domain, we cannot say f is going to be onto. But if cardinality of A is not greater than or equal to cardinality of B, that is, if cardinality of A is less than cardinality of B, then you cannot define any onto function from A to B. Similarly, if cardinality of A is greater than cardinality of B, you cannot define any one-one function from A to B. If cardinality of A is strictly greater than cardinality of B, means if cardinality of the domain is greater than cardinality of the codomain, you cannot define any one-one function from A to B. So necessarily for a function to be 1, 1 from A to B, cardinality of domain A should be less than or equal to cardinality of the codomain. For a function f to be onto from A to B, cardinality of the domain should be greater than or equal to cardinality of the codomain. Please note that these are only necessary conditions, not sufficient. Just because of the fact that cardinality of the domain is less than or equal to cardinality of B, we cannot say function is onto. Just because of the fact that cardinality of A is greater than or equal to cardinality of B, we cannot say function is onto. Then you have to go for checking them either graphically or through analytical. But if cardinality of A is not less than cardinality and less than or equal to cardinality of B, certainly there is no one-one function. If cardinality of A is not greater than or equal to cardinality of B, certainly there is no one-one function from A to B. So this is what one function and onto function, that is injective and surjective function. Now let me go for similarity of sets. Similarity of sets. Similarity of sets. Please note that if A and B are any two subsets of real line, and if there is a bijection, that is one function, one-oneness and onto-ness between A and B, then we say A and B are in one-to-one correspondence. One-to-one correspondence. We say two subsets of real line A and B are in one-to-one correspondence if and only if there is a bijection, at least one bijection between them. If there is at least one bijection between A and B, then we say A and B are in one-to-one correspondence. One-oneness is different, one-to-one correspondence is different. One-to-one correspondence means between two sets means there has to be some bijection between those two sets. That is what is the meaning of one-to-one correspondence. One-to-one correspondence. Now let us see, when do we say two sets are similar? When do we say two sets are similar? So let A and B be any two subsets of real line. We say two sets A and B are similar if they are in one-to-one correspondence. If they are in one-to-one correspondence, means if there is a bijection between A and B, then we say A and B are in one-to-one correspondence. So if A is similar to B, then there is a bijection between, there is at least one bijection between them. At least one bijection between them. If there is at least one bijection between them, there has to be a one-one function from A to B, and there has to be an onto function from A to B. But by necessary condition of one-one function and onto function, we know that if there is a one-one function from A to B, cardinality of A is less than or equal to cardinality of B. And if there is an onto function from A to B, then cardinality of A is greater than or equal to cardinality of B. By combining both the results, cardinality of A is equal to cardinality of B. That means if there is a similarity between two sets, their cardinalities must be same. And converse is also true. Means if cardinality of two sets is same, then those two sets are in one-to-one correspondence, and hence they are similar. That's why similar sets are also called equipotential sets, equinumerous sets. Equipotential sets, equinumerous sets, or equivalent sets, or similar sets. All are same. Similar sets, equivalent sets, equipotential sets, equinumerous sets. All are same. So this is an if and only if condition. If A and B are similar, their cardinalities are same. If their cardinalities are same, they are said to be similar. You may ask, sir, what happens in the case of infinite sets? In the case of infinite sets also, the same definition holds. That means two sets, whether they are finite or infinite, both are finite or infinite. Certainly, finite set and infinite set cannot be similar because their cardinalities will be different. But if both are finite, obviously we can verify whether there is a similarity between those two sets or not by knowing whether their cardinalities is same or not. But when they are infinite sets, that is a challenging task. Whether to show whether there is a similarity between two sets or not, it is a challenging task. So this task was made easy. This challenge was made easy by a great mathematician, George Cantor, but through his publication in 1873, famous and landmarking publication in the year 1873. Since then, classification of infinite sets and cardinality of infinite sets has got some meaning and some fruitful meaning. Before that, people used to think that all infinite sets are of same cardinality. So there were a lot of confusion among the mathematicians only about this topic, whether all infinite sets are of same cardinality or not. So Euler made a systematic effort and brought out with a conclusion famously called as Cantor's theory of transfinite numbers, or Cantor's theory of transfinite number. He came up with certain symbols to denote cardinality of infinite sets and concluded that there are infinite number of infinite sets. People earlier used to think that all infinite sets are of same cardinality, and there were certain contradictions as well. But nobody had a clear-cut valid discussion conclusion about this aspect. But he made a systematic effort, systematic study, and came up with a theory that is called transfinite number theory. In this transfinite numbers, what he did is these are not the numbers. Please note this: transfinite numbers, what George Cantor suggested, are not real numbers or any kind of number. They are just the symbols used by George Cantor to denote cardinality of infinite sets. And he concluded that cardinality of infinite sets, all infinite sets are not same. And in fact, there are infinite number of infinite sets. There are infinite number of infinite sets. And he concluded that the smallest infinite set is the set of counting numbers, that is natural number set, the basic counting set, that is natural number set. Natural number system, all of you are well aware of these things. So it came naturally to the human civilization since beginning. So that's why it is called natural number system. So this natural number system is what we call it as basic counting set. And he proposed a symbol to denote the cardinality of this basic infinite set, or fundamental infinite set, or first infinite set, or smallest infinite set, that is called set of natural numbers. And he called this as a basic counting set, and he proposed a symbol to denote the cardinality of this basic counting set by a symbol called by the name Aleph naught. One minute. Aleph naught. Just a minute. Some technical error. So transparent numbers are the symbols, not the numbers. Please note this point, used by George Cantor to denote the cardinality of infinite sets, and he concluded that there are infinite number of infinite sets. The first smallest infinite set is the basic counting set, that is the set of natural numbers, and he proposed a transfinite number, that is a symbol, to denote the cardinality of the set of natural numbers, that is denoted as Aleph naught. Aleph naught. Aleph naught. This is the symbol used by George Cantor to denote the cardinality of basic counting set, that is natural number, and this natural numbers is the smallest infinite set. Smallest infinite set. Smallest infinite set. And he came to know that if n is the infinite set with cardinality of n is equal to Aleph naught, then certainly if I find its power set of natural numbers, this is going to be a set of cardinality 2 to the power of Aleph naught, because all of you know that if A is a set with n elements, then its power set is going to have 2 to the power of n elements. That is also true in the case of infinite cardinals as well. If cardinality of n is Aleph naught, then cardinality of its power set is 2 to the power of Aleph naught. And certainly from any set to its power set, there cannot be any one-to-one correspondence. From any set x to its power set, that is p of x, there cannot be any bijection. There cannot be any bijection. There cannot be any bijection. So because of this fact, so any set, whether it is finite or infinite, and its power set are not similar, because their cardinalities are not same. Their cardinalities are not same. Hence, there is no bijection or one-to-one correspondence between any set, whether it is finite or infinite, to its power set. Hence, he concluded that, oh, there are still even bigger infinite sets which have more elements than that of n. Because P of n is an infinite set having 2 to the power of alif naught number of elements. 2 to the power of alif naught is always greater than alif naught, 100%. So therefore, he thought that P of n is an infinite set having more elements than the infinite set n. Then he came up with a conclusion that likewise, there are infinite number of infinite sets. Infinite number of infinite sets. To denote the cardinality of a set which is uncountable, I will explain what is that uncountable and uncountable. He used a symbol called alif 1 or continuum. Alif 1 or continuum. Just use a symbol to denote the cardinality of any cardinality of uncountable set. An uncountable set is always similar to the set of real numbers. I will explain. Just wait. Is always similar to the set of real numbers. Any set whose cardinality is similar to the set of real numbers is always uncountable. Is always uncountable. Now, to denote the cardinality of uncountable set, use this symbol alif 1. Similarly, alif 2, alif 3, alif 4, and so on. I will explain what are those. To denote the cardinality of a countable set, use finite cardinals and one infinite cardinal. Infinite cardinal is alif naught. Finite cardinal means 0, 1, 2, 3, and so on. Because if cardinality of a set is 0, that means if a set is empty set, its cardinality is 0, and 0 is called finite cardinal number. If a set is a singleton set, its cardinality is 1, then it is 1 is the finite cardinal number. Similarly to finite cardinal number, and so on, so on. The smallest infinite cardinal is alif naught. Among the infinite cardinals, there are two types of cardinal numbers: finite cardinal numbers and infinite cardinal numbers. To denote the cardinality of a finite set, we use the numbers 0, 1, 2, 3, and so on, n and so on. But to denote the cardinality of infinite set, George Cantor suggested some symbols called transfinite numbers. They are not the numbers, they are actually the symbols used by George Cantor. The smallest such infinite cardinal number is given by alif naught, because natural numbers is the smallest infinite set. Hence, its cardinality is going to be the smallest infinite cardinal number. Smallest infinite cardinal number. And they are related by the relation 0 less than 1, less than 2, less than 3, less than 4, and so on, so on, so on, less than, and so on, so on. Less than alif naught. Up to less than alif naught, all cardinal numbers are finite cardinal numbers. Finite cardinal numbers up to alif naught. But from starting with alif naught, alif 1, alif 2, etc., etc., these are going to be infinite cardinal numbers. And smallest such infinite cardinal number is alif naught. Alif naught. So, to denote the cardinality of natural numbers, use the symbol alif naught. To denote the cardinality of real number system, use the symbol alif 1 or continuum. To denote the cardinality of P of R, use the symbol alif 2. To denote the cardinality of P of R, use the symbol alif 3. To denote the cardinality of P of R, use the symbol alif 4, and so on. Because power set, right, and original set X and its power set are not in one-to-one correspondence. Cardinality of P of X is more than that of cardinality of X. So here, cardinality of R is denoted by alif 1 or continuum. Its power set, that is cardinality of P of R, is going to be 2 to the power of alif 1 or 2 to the power of continuum. But you might have seen in your topology class, for those who are studying in MSc, we have proved that, or we are going to prove that 2 to the power of continuum is greater than continuum. To denote continuum, use the symbol alif 1. To denote 2 to the power of continuum, use the symbol alif 2. To find what is cardinality of P of R, and it is going to be 2 to the power of alif 1. 2 to the power of alif 1. Sorry, 2 to the power of alif 1. That comes out to be alif 2, and so on. So likewise, he came up with a conclusion that there are infinite number of infinite sets. Among those infinite sets, smallest infinite set is natural number set. So this is what is theory of transfinite numbers suggested by George Cantor, and it is the most if not 100%, the most successful classified theory which gives or which throws a light on cardinality of infinite sets. Most successful and most most authenticated, if not 100%, theory about the cardinality of infinite sets. That is what suggested by George Cantor, that is transfinite number, theory of transfinite numbers. Now, moving on. Now let us see some examples for similarity of sets. N and 2n. Let us take it as A and B as 2n. At the outset, if we look into both the sets A and B, you may wonder, you may think that n has more elements than that of 2n, because 2n consists of only even natural numbers, but n consists of both odd and even natural numbers. You may think that, or you may force it to think that, or conclude that, so cardinality of n is greater than cardinality of 2n, because 3 does not belongs to n, 2n, 5 does not belongs to 2n, and so on, so on. Hence, you may compel to conclude that, oh, cardinality of n is more than that of cardinality of 2n. Actually, it is wrong. These two sets are similar. This is where you need to understand the difference between similarity between two finite sets and similarity between two finite sets. Of course, both are going to be means final conclusion is same. If both are having same cardinality, they are going to be similar. But when we look at the cardinality of n and cardinality of 2n, one may think that cardinality of n is greater than cardinality of 2n, but in reality, cardinality of n is same as that of cardinality of 2n. Cardinality of n is same or equal as that of cardinality of 2n. How to prove this one? To prove that these two have same cardinality, we have to show that these two are similar. So to prove there is a similarity between n and 2n, just it is enough if we can show n and 2n members are in one-to-one correspondence. So for that, it is enough to define a bijection between n and 2n. Any one bijection, not more than any one bijection between n and 2n would be sufficient enough to conclude that n and 2n are in one-to-one correspondence. So let f from n to 2n, I'm going to define like this. Be a mapping defined by f of n is equal to 2n. F of n is equal to 2n. You can easily verify that this mapping is going to be bijective. Just the method of proving one-oneness and two-ness I explained. So I will leave it to you. I am not going to look into that part. Clearly, this function is one because different elements in domain have different images in codomain. But if you take any element of codomain, it's half of that element. Half of that element is going to act as pre-image of that particular element. So every element in codomain has at least one pre-image in domain. Hence, f is going to be injective as well as surjective. Hence, f is going to be bijective. Therefore, n and 2n are in one-to-one correspondence. N and 2n are in one-to-one correspondence. Or else you can verify like this. Rough calculation. 1, 2, 3, 4, 5, 6, and so on. Here 2, 4, 6, 8, 10, and so on. These are the members of 2n and these are the members of n. What is the connection? If I take n is equal to 1, it will be mapped onto 2. 2 will be mapped onto 4. 3 will be mapped onto 6. 4 will be mapped onto 8. 5 will be mapped onto 10, and so on. Clearly, different elements have different images here, and all elements have pre-images. If no member is left out in the codomain having no pre-image. All elements of codomain have pre-images. You can verify like this as well, especially when the sets are discrete like this. So clearly f is going to be bijective. So that means n and 2n are in one-to-one correspondence. Therefore, cardinality of, if they are in one-to-one correspondence, this mapping is bijection. That means cardinality of n is less than or equal to 2n. Cardinality of 2n is less than or equal to n, because 1 and onwards. From this, we can conclude that cardinality of n is equal to cardinality of 2n. Hence, n and 2n are similar, are equipotential, are equinumerous. Let me give you one more example. N and z. What about n and z? Are their cardinalities different? Are their cardinalities same? Means are they similar or not? Even though you may think that all integers are not natural numbers. Therefore, Z has more size than that of N. Z has more size than that of N. You may think like, but in reality, N and Z are similar sets. Means both are having same size. Both are having same size. So therefore, similarity is altogether a different concept. Similarity is altogether a different concept. Similarity means not just two sets need not have the same numbers, need not have the same members for similarity. One set may have any kind of elements, objects, or another set may have any kind of objects. The only thing is whether they are similar or not can be verified by knowing whether they are having same cardinality or not. So here, members of N, all members of 2N are not in, but all members of N are all members of 2N are not in 2N, but all members of 2N are in N. You may think that since many members of N are not in 2N, they may have different color. In reality, it is not so. Because members of N and 2N are in one-to-one correspondence. Means for every N, there is a unique 2N, a member of 2N. For every member of 2N, there is a unique member of N. That means one-to-one correspondence. So if there is one-to-one correspondence between two sets, certainly their cardinalities has to be same. So here, cardinality ನೋಡಬೇಕಾದಾಗ same elements ಇರಬೇಕು ಅಂತ ಏನಲ್ಲ. One set ಅಲ್ಲಿ objects ಬೇರೆ ಇರಬಹುದು, ಇನ್ನೊಂದು set ಅಲ್ಲಿ objects ಬೇರೆ ಇರಬಹುದು. Only the thing is, for every element of A, is it possible to associate a unique element of B and vice versa? If that is possible, that means they are in one-to-one correspondence. If they are in one-to-one correspondence, obviously they are equanimous. That means they are having same cardinalities. Now, let us see whether N and Z are similar or not. Obviously, these two are similar. So how do we establish similarity from N to Z? Define a mapping like this. F of N is equal to N minus 1 by 2 if N is odd, minus N by 2 if N is even. Now, this is clearly a bijection. Why? What is your domain N? Take 1, 2, 3, 4, 5 for easy calculation, for easy and quick conclusion. So 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, etc. When N is odd, put N is equal to 1 here. 1 minus 1 by 2, that means 1 is connected to 0. Next, N is equal to 2, 2 is even. Minus 2 by 2, that is minus 1. 2 is connected to minus 1. 3 is connected to 1. 4 is connected to minus 2. 5 is connected to 2. 6 is connected to minus 3. 7 is connected to 3 and so on. See, look at this correspondence. Different elements in domain are going to have different images in codomain. And none of the element of codomain is left out in this range. Means all elements in codomain. Means every element in codomain has at least one image. So there is one-to-one correspondence. Because there is a bijection between this N and 2N. This is the bijection. I don't want any number of bijection. Just I want one bijection of any type. One bijection. I need just one bijection between N and Z, or from Z to N. If you can show that there is at least one bijection between N to Z or N to Z to N, that means they are in one-to-one correspondence. That means they are similar, equinumerous, equipotential. So defining a bijection between two sets is need not be unique. You can define in plenty of ways. I don't want any number of bijections. Just I want one bijection between two sets to conclude that they are in one-to-one correspondence. Means they are similar. That means they are having same cardinality. So this is what is the meaning of similarity of sets. Now we are ready to define what is a finite set and what is an infinite set, because all of you know what is finite and infinite set, but in different way we are going to redefine what is finite and infinite set. So let us define or look into what is the difference between finite and infinite sets. Infinite set. Please note that a set A is said to be finite. A is said to be finite if cardinality of A is strictly less than alif naught. If cardinality of A is strictly less than alif naught, because I told you already, N is the smallest infinite set. Therefore, if any set is having cardinality less than the cardinality of alif naught, it has to be finite. Therefore, a set A is said to be finite if and only if its cardinality is strictly less than alif naught, because alif naught is the smallest infinite cardinal. Any cardinal number less than alif naught will always be a finite cardinal number. I explained already. Finite cardinal number. That means cardinality of an finite set. So using this information, we can redefine finite sets and infinite sets using alif naught concept. That is, a set A is said to be finite if cardinality of A is strictly less than alif naught, because alif naught is the cardinality of the smallest infinite set. Therefore, any set having cardinality less than that of natural number, that is alif naught, certainly has to be a finite set. Therefore, a set A is said to be finite if and only if cardinality of A is less than alif naught. And when do we say A is infinite? If it is not finite. That means if cardinality of A is either alif naught or greater than alif naught. If cardinality of A is either alif naught or greater than alif naught, means if cardinality of A is equal to that of natural numbers or more than the cardinality of natural numbers, then A is going to be an infinite set, because n is the smallest infinite set now. There are infinitely many infinite sets are there. So if any set is having cardinality more than the cardinality of infinite set, certainly it has to be infinite. Because a basic counting set, that is natural number set, we regard as the smallest infinite set, and its cardinality is alif naught. Any set having cardinality more than that of n certainly has to be infinite. Therefore, cardinality of A is greater than or equal to alif naught implies A is infinite. This is an alternate way of defining finite and infinite sets, because usually in our elementary number set theory of our high school or PUC, we define like this. If a set A has finite number of elements, starting 1, 2, 0, 1, 2, 3, and so on, that is finite like that. If it is not finite, then it is infinite. This is what the definition we have come across in our school days. But since you are undergraduate and postgraduate student, you need to think it in a different way. Because we are going to expose to the different higher level concept, that is transfinite theory proposed by George Cantor. That's why it's called father of modern set theory. So if cardinality of A is less than alif naught, A is finite. Otherwise means greater than or equal to alif naught, A is said to be infinite set. This is what is the difference between finite set and infinite set. Now we are going to define a special kind of set that is called denumerable set. Denumerable set, or also called as countably infinite set. Countably infinite set. Denumerable set or countably infinite set. Denumerable set or countably infinite set. A set is said to be countably infinite or denumerable if A is similar to n. Please note this point. If A is similar to n, then A is said to be countably infinite or denumerable. Very important definition. If any set having cardinality similar or equal to that of natural numbers, then such a set is said to be denumerable set or countably infinite set. Countably infinite set. That is, A is said to be denumerable if cardinality of A is equal to alif naught. If cardinality of A is equal to alif naught, that is nothing but cardinality of natural number, then A is similar to n. If any set A is similar to the natural number set, or if any infinite set is similar to the natural number set, then A is said to be denumerable set. Countably, not greater than alif naught, exactly alif naught. Exactly alif. Because of this fact, n and 2n have same cardinality, because already I have shown that these two are similar. So therefore, cardinality of n is alif naught, therefore cardinality of 2n is also alif naught. Therefore, cardinality of z is also alif naught. Please note this point. Cardinality of z is also alif naught, because n and z are similar. They are in one-to-one correspondence. Hence, they must have same cardinality. Therefore, n and z are having same cardinality. Therefore, cardinality of z is alif naught. Now, we are ready to define what is countable and what is uncountable set. What is countable set and an uncountable set. Countable set and uncountable set. A subset of real line R is said to be countable. Is said to be countable. Is said to be countable if either A is is said to be countable if cardinality of A is less than or equal to R. I'm sorry. A subset A of R is said to be countable if and only if cardinality of A is less than or equal to R. Please note this point. Here, there are three subcases. If cardinality of A is less than or equal to F naught, cardinality of A may be 0. Cardinality of A may be finite but non-zero. Finite but non-zero. And cardinality of A may be F naught. These are the three possible cases here. When we have the condition that cardinality of A is less than or equal to F naught, either cardinality of A may be 0 or cardinality of A may be finite real number, but finite natural number, but not equal to 0, finite positive integer, but not 0, and cardinality of A may be F naught. These are the three possibilities. If cardinality of A is 0, then A is going to be empty. If cardinality of A is finite, then A is going to be a finite set with minimum one element, with finite set with minimum one element. And if cardinality of A is F naught, then A is going to be denumerable. Denumerable or countably infinite. Countably infinite. Denumerable or countably infinite. Therefore, a subset A of R is said to be countable either it is empty, or it is finite having at least one element, or if it is countably infinite. In all the three cases, we say A is a countable set. A is a countable set. But there are two schools of thought as far as this definition is concerned. As far as the definition is concerned, there are two schools of thought. Some school of thought think that countable means only denumerable. So these are finite sets like. So, but most of the others, 99% of the people use this as the definition of countable set. Some others just denumerable set countable and but most of the others we follow this definition. Therefore, because this happened a few years back when there was a question in CSIR NET exam, they set the options keeping the second definition in mind. But most of the universities and colleges in India, we people teach this definition. Even in 99% of the books also, we follow this definition. That's why students subjected to the options given by the CSIR, then it rectified, and later on grace marks were given to the students. So most of the books and most of the almost all books and almost all teachers follow this definition. That's why I am also sticking out to this definition. This is a word of caution I wanted to tell you. So this is what is the definition of countability. Countable set. So what does countability means? Okay, this is if A is countable, if cardinality of A is less than or equal to F naught, or that is if A is empty or a finite with at least one element, or a countable infinite, then A is countable. Fine, this is available in your text. But what actually it means? So countability has following meanings. The term countable, the word countable has following meanings. The term or the word countable has following meanings. As following meanings. First one is countable means every element of the set has a definite successor. You know what is successor? Predecessor, successor. Predecessor means previous element, successor means next element. One must be able to identify successor for each and every element of the given set. If this is possible, then such a set is countable. What next after this element? You must be in a position to identify. What next after this element? You must be in a position to identify. If that is possible for each and every element of the given set, then such a set is said to be countable. I repeat, if it is possible to identify successor for each and every element of the given set, such a set is countable. If I take natural numbers, if I say, who is the successor of 1? Without any confusion, you say 2 is going to be the successor of 1. Who is going to be the successor of 3 in the calendar? You will say 4 is going to be the successor of 3. If I ask, who is the successor of 1001? You will say 1002. So that means you are able to find or identify successor for each and every element of this natural number set. That is what something is countable. If this is not possible, if this identification is not possible for at least one element of the given set, that is not countable. If I ask, what is the next real number? What is the real number? What is the next real number? Or what is who is the next real number of 0? If I take 0, who is the next real number? If I ask, you can't say. Because the moment you say 0.0000000 100 times 01, I can show infinitely many real numbers between 0 and 0.00000 100 times 0. Means I am unable to find a real number greater than 0, the next real number greater than 0. If I ask, who is the next real number greater than 1.2? Who is the immediate next real number greater than 1.2 or 0.5? I cannot say. If I say 0.5555555 100 times or 1000 times or 1 lakh times 5, between 0.5 and 0.555, that is 5 lakh times 5, I can show infinitely many real numbers. That means you cannot tell me who is the next real number, that next adjacent real number to 0. Who is the next real number of 0.5? No, you cannot say. That is what is called as uncountable. If that identification of successor is not possible for at least one element of the given set, then the set is not countable. Then the set is not countable. This is what is the meaning of countability. So first meaning of the countability means what? It is if it is possible to identify who is the successor for each and every element of the given set. Each and every element of the given set. That is what is countable. If this type of identification is not possible, such a set is to be uncountable. So generally, students or many people think that, oh, infinite sets means uncountable, finite sets means it is countable. No, it is not like that. It is not like that. If I ask who is the next real number of 1, I will say 2. Who is the next one? 3, 4, 5, 6. Means I am able to identify the successor for each and every element. Means I can list out all the members by identifying the successors. If this is possible, something what is called as countable. Then what is uncountable? If this process is not possible. If this process of identifying the successor and listing them from the beginning, if this is not possible, that is called uncountable. Let us see other way. How can we interpret countability in another way? Countability means it should be possible for us to arrange the members of the set, given set, in the form of a sequence. If it is possible to arrange the members of, if it is possible to arrange the members of the given set, in the form of a sequence, then such a set is said to be countable. First one is if every element of given set, has a definite successor, This is also countable. This is also countable. So sequence. A sequence is a function from natural numbers to real numbers. A sequence is actually a function from natural numbers to real numbers. 1, 2, 3, 4, 1, 2, 3, 4, and so on. We are going to assign a real number x1. We call it as x2 or the image of 2. We call x3 as the image of 3. We call x4 as the image of 4, and so on. And we write them as x1, first member means image of 1 as the first member of the sequence, and image of 2 as the second member of the sequence, image of 3 as the third member of the sequence, image of 4 as the fourth member of the sequence, and so on. This is what is sequence, sequence of real numbers. Then the countable set means what? The given set is said to be countable if it is possible for you to arrange the members of the given set in the form of a sequence according to the any rule of your desire. You can decide any rule. Have your own rule, no problem. But according to the rule you have chosen, you must be in a position to identify who is the first member according to the rule of the given set. According to the rule I have chosen, who is going to be the second member, who is going to be the third member according to the rule I have chosen. Whatever the rule you choose, that is left to you. That is left to you. You are free enough to choose any rule you want. But once the rule is decided, you must be able to say who is the first member according to your rule of your set, who is the second member of your set according to your rule, who is the third member of the set according to your rule, who is the 100th member of your set according to your rule. If I ask who is the 1000th member of your set according to the rule you have chosen, you must be in a position to say, oh, this element is going to be the 1000th element according to the rule I have chosen. If this is possible to identify, means if it is possible to arrange the members of your set in the form of a sequence. In a sequence, if I say who is the first member, you will say x1. In the sequence, if I say who is the second member, you will say x2, you will say x3, you will say x100, and so on. That means you are able to identify successor for each and every element. If that is possible in your set, if that is possible in your set, that set is going to be countable. If that is not possible, means if it is not possible to arrange the members of your set in the form of a sequence, such a set cannot be countable. That is what is called as uncountable. So sometimes you can decide whether the given set is countable or not by verifying whether the elements of the given set can be arranged in the form of a sequence in any fashion we want, or in using any rule we want. If it is possible to define a rule, means find a rule. And if it is possible to list out the elements of your set according to the rule as a first member, second member, third member, fourth member, and so on, then that is countable. You need not define bijection. There itself, there is a bijection. You need not define bijection. If you can identify certain rule, using that rule, if you are able to say list out who is the first member, who is the second member, who is the third member, and so on, that itself is countable. If this is not possible, that set is uncountable. This is simple meaning of countability or countable set. So all these three definitions have same meaning, means all are equivalent. 1, 2, 3, all are equivalent. This is what is DS1, this is what is countability. A set which is not countable is called uncountable. That means if it is not possible to identify a successor of a particular element, or if the elements of the given set cannot be arranged in the form of a sequence using any rule, then that set is not going to be countable. That is what is uncountable. Let us take an example, say n cross n. Whether n cross n is countable or not. Cartesian product of n natural numbers. Whether it is going to be countable or not, let us see. The members of n are, I think, 1, 1, 1, 2, 1, 3, 1, 4, and so on. I can write like this: 2, 1, 2, 2, 2, 3, 2, 4, and so on. 3, 1, 3, 2, 3, 4, and so on. 3, 3, 3, 4, and so on. Now, I want to verify whether this set is countable or not. Just I'm going to use this, any one of this type. This one, whether it is possible to list out the elements of the given set in the form of a sequence. If it is possible to identify the members according to certain rule as first member, second member, third member, and so on, that means it can be arranged in the form of a sequence. That means such a set is countable. Now, choose any rule you want. It is not necessary that you have to follow my rule. There is no necessary that you should follow the rule I am going to give. Any rule you want, but you stick on to the same rule throughout your set. And according to your rule, you must be identified who is the first member, who is the second member, who is the third member, who is the fourth member, and so on. So on. If this is possible, that is what is countable. Now, what I'm going to give you here. I'm going to arrange these members, which are in the ordered pairs, in such a in the increasing order of their sum. If the increasing order of their sum means if I add x coordinate and y coordinate, the sum I am going to get. In the increasing order of the sum, I am going to arrange these members. If any two ordered pairs are having same sum, then I will give preference to that ordered pair which has larger x coordinate than the y coordinate. This is my rule. This is my rule. I am telling you, you need not follow this rule. You may have your own different rule. You may have your own rule. But whatever the rule you choose, you stick on to that throughout your set. Now, I have suggested one rule. Arrange these numbers in the increasing order of their sum. And if any two ordered pairs are having same sum, give preference to that ordered pair in which the x coordinate is more than that of the y coordinate. Now, here for this element, I am going to get the sum 2. So therefore, first member is 1, 1. According to my rule, first member is 1, 1 because all other elements are having sum more than 2. This is the only element having sum 2. Because all remaining ordered pairs are having sum greater than 2. That's why, according to my rule, this is the first member. 1, 1 is the first member. Now, if you look at the elements on this diagonal, 2, 1 and 1, 2, both are having same sum. Both are having same sum. Now, 3, here sum, here also sum 3. Now, but I will, if any two or more ordered pairs are having same sum, I will give preference to that ordered pair which has larger x coordinate than the y coordinate. So here 2, 1, because here x coordinate is more than that of y coordinate. Then 1, 2. So next, go here. Larger x coordinate is 3, 1. Then 2, 2. Then 1, 3. See, according to the rule I have chosen, I can easily arrange these numbers. It is not necessary that you should follow this rule only. You can have your own rule, any different rule. Excuse me, can you please mute your? Right? So therefore, according to any rule of our choice, if we are able to arrange the members in the form of a sequence like first number, second number, third number, that's satisfactory. I can give you one more rule. I'm going PQ. Here, let PQ be the qth member of P plus Q minus 1th row. This is first row, this is the second row, this is the third row, this is the fourth row, fifth row, and so on. Now, 1, 1. 1, 1. Let PQ be the qth member of P plus Q minus 1th row. P plus Q minus 1th row. Right. So here, this is first row, first element, because here P is 1, Q is 1. First member of 1 plus 1 minus 1. That is first row, first member of first row. I will choose this as a first member. That is this Q value, qth member. In the increasing order of Q, I am going to arrange these members. Who is the first member? First member of first row. Means who is the first member? Means I want the first member. First member of first row means by taking P as 1. Sorry, P plus 1, P plus Q minus 1. If I take 1 and 1, 1, 1 is going to be the first member of first row. I am going to choose this as the first member. Who is the second member? Next, second member of first row. Second member of first row means what? So 1, 2, 1 plus 2 minus 1, 3 minus 1, 2. Here 1, 2 is going to be my second member. Likewise, I am going to arrange. This is another rule. Or else, if you don't want this one, what you do is from n to n cross n, from n to n cross n, define a mapping like this. Like f of P comma Q is equal to P plus Q minus 1 into P plus Q minus 2 divided by P plus Q minus 2 plus Q. Or we define like this. f of p comma q is equal to p plus q minus 1. Sorry, n cross n to n. I'm sorry, n cross n to n. Define a mapping by f of p comma q is equal to p plus q minus 1 into p plus q minus 2 divided by p plus q. Sorry, by 2. Sorry, not 2. P plus q minus 1 into p plus q minus 2 by 2 plus q. You can verify it is going to be 1, 1 and 2 bijective. I will leave it to you. The portion of proving bijectivity. So this is going to be bijective. Since there is a bijection between n cross n to n cross n is equivalent to n or similar to n. Since n cross n is similar to n, since n is countable, n cross n has to be countable. Because then cardinality of n cross n must be same as that of cardinality of n, because these are similar, but cardinality of n is alif naught. So therefore cardinality of n cross n is also alif naught. If any set is having cardinality either alif naught or less than alif naught, if any set is having cardinality either less than alif naught or equal to alif naught, then such a set is always countable. Hence, n cross n is countable. This is other way of showing the given set is countable. N cross n is countable. One more way is by using any rule, choosing any rule, arranging the members of n cross n according to the rule in the form of a sequence. N cross n is going to be countable. On the same lines, you can prove that z cross z is also countable. Z cross z is also countable. And the same lines you can prove that z cross z is also countable. So using that algebra of transfinite numbers also, we can easily come to know that whether z cross z or n cross n is countable. This is an alternative technique I am going to give. So if it is difficult for any student, you need not follow this, because those students who are having a little bit higher knowledge about cardinality of transfinite numbers, they can easily follow this. But I am going to give you both the proofs. I have already given the proof of n cross n is countable using first principle technique. But using cardinal numbers also, you can come to know that n cross n is countable. Alif naught to the power of any natural number is going to be alif naught. Please note this. That's why I'm not going to prove these things. These are available in your books. This is an alternate approach I'm going to give, shortcut method, alternate approach. That's why I'm not going for the proof of these things. But basically, using the definition of countability, we can show f is n cross n is countable like this, which I have explained. Now, what I'm trying to give you is a shortcut way of verifying whether the given set is countable or not using the cardinal numbers. Alif naught to the power of any natural number is going to be alif. We know that if A and B are any two sets with cardinality of A and cardinality of B, then A cross B, cardinality is going to be cardinality of A into cardinality of B. Cardinality of A cross B is equal to cardinality of A into cardinality of B. This is what we. Here, n cross n. What is cardinality of n cross n according to this one? It is going to be cardinality of n into cardinality of n. What is cardinality of n? Alif naught. What is cardinality of n? Alif naught. So alif naught into alif naught is alif naught square. Alif naught square is alif naught. For any natural number n belongs to n, alif naught to the power of n is going to be alif naught. This is a result which I am not going to prove here, just because I am giving you a shortcut method. That's why I straight away I am giving this result. If you want, you can follow any books on basic topology. That is basic topology book, if it is available in always in your library. You can go through these things for the proofs of these results. Similarly, cardinality of z cross z is also alif naught, because this is cardinality of z into cardinality of z. But already I have shown that n and z are similar. Therefore, both are having same cardinality. Therefore, cardinality of z is alif naught. Cardinality of z is alif naught. Then z is going to be alif naught square. That is alif naught. Since cardinality of z cross z is alif naught only, z cross z is countable. Z cross z is countable, because any set having cardinality less than or equal to alif naught is going to be countable. This is an alternate approach, or in a short span of time you can identify whether it is going to be countable or not. Now, I'm going to take up one or two results, which is very important. If A is a countable set, result or theorem. If A is a countable set and B is a subset of A, what can you say about B? What can you conclude about B? If A is countable and B is a subset of A, whether B is countable or not? That is the question. Answer to this question is yes, B is always countable. Every subset of a countable set is always countable. Every subset of a countable set is countable. Proof is very simple. Let A be a countable set. Let A be a countable set. For the sake of simplicity, I am just following the proofs of NP Bali, which is sufficient enough for graduate students. For the sake of simple understanding, I am choosing this proofs because it will be able for it will be easy for a student of undergraduation to comprehend or understand these proofs. That's why I am choosing the simplest proof that is available in NP Bali book. If you want, I can refer that. Let A be a countable set. That means either A is finite, or A is empty, or A is countably infinite. Countably infinite. Three possibilities are: A is a countable set, means either it could be empty set, or it could be finite set, but having at least one element, or it could be countable infinite set. In all other cases, in all these three cases, we can prove B is countable. First subcase, if A is equal to 5, certainly B is equal to 5. Then B is also countable. So in this case, the result is direct. Second one, if A is finite with minimum one element, certainly B, subset of a finite set, is also finite. Therefore, B is also countable. Every subset of a countable set, finite set is finite, na? Every subset of a finite set is finite. Therefore, B is also finite, hence countable. Third one, if B is infinite, but subset of infinite subset of A. If B is infinite subset of A, then A cannot be finite. B being a subset of A, infinite subset of A, then A cannot be finite. A has to be countably infinite, because A is already countable. No? A is countable but cannot be finite. That means A is countably infinite. So A is countably infinite. Here A is countably infinite. A is countably infinite. But B is a subset of A. So please think that if B is a subset of A, where A is countably infinite, that means A is similar to N or equivalent to N. A is equivalent to N. B is a subset of N, but B is also infinite. That means B also has infinite elements, A also infinite elements, but A being similar to N can be arranged in the form of a sequence. Members of A can be arranged in the form of a sequence, like A1, A2, A3, A4. Members of A can be arranged in the form of a sequence, like A1, A2, A3, A4, A5, and so on, because A is countably infinite. Therefore, members of A can be arranged in the form of a sequence like A1, A2, A3, and so on. But B being a subset of A, at some stage, for at least one N1, at least for some N1, the corresponding AN1 must be in B. ಇದರಲ್ಲಿ ಯಾವುದೋ ಒಂದು ಎಲಿಮೆಂಟ್ B ನಲ್ಲಿ ಇರಲೇಬೇಕಲ್ವಾ? Let that element be AN1 corresponding to N1. Just hold on, dear student. So A being a countable infinite set is similar to N, therefore its members can be arranged in the form of a sequence like A1, A2, A3, and so on. But B being an infinite subset of A, some members of A must be in B. If not all members of A are in B, some members of A must be in B. In fact, infinitely many members of A must be in B, because B is infinite. So then there has to be some member of A that is going to be the first member of B. Means there exists at least one N1, then there exists a first positive integer N1, such that the corresponding element AN1 of A belongs to the set B. That is what. Let n1 be the least positive integer. Let n1 be the, suppose a1, a2, a1, a2 are not in B. Then, and if a3 is in B, then 3 is the least positive integer such that a3 belongs to B. Suppose if a1, a2, a3 are not in B, because possible, na? B is a subset of A. a1, a2, a3, if they are not in B, then a4 is the first member of a4 is the member of A which is in B. That means 4 is the least positive integer such that the corresponding a4 belongs to B. That's what I am going to write here. Let n1 be the least positive integer such that an1 belongs to B. But B is infinite. The single element cannot be equal to B. Means there has to be one more element of A. It has to be in B. One more element of A has to be in B because B is infinite. And let n2 be the least positive integer greater than greater than n1 such that an2 belongs to B. So if an1 belongs to B, certainly B cannot be a singleton set because B is infinite. That means one more element has to be there in A which is a member of B. So then there may be another suffix n2 which is the least positive integer such that an2 belongs to B where n2 is greater than n1. If you continue this process, because again now here B consists of two elements, that is an1 and an2. This is not possible because B is infinite set. But here in this collection we are having only two elements. So that means we have to go, there has to be at least one more element of A which should be a member of B. Let that member be an3. So then n3 is the least positive integer such that n3 greater than n1, n3 greater than n2 such that an3 belongs to B. So n3 be the least positive integer greater than n1 as well as greater than n2 such that an3 belongs to B. Now in this process we have collected three elements an1, an2 and an3. Certainly this cannot be equal to B because B is infinite. So therefore continue this process of choosing members from A which should be the members of B like this. If you continue this process, we are going to get a set B infinitely many times. We are going to get the members of B as first member we have selected is an1, second member is an2, third member is an3 and so on. So B is also. Now from B to A, let us define a mapping, or A to B, let us define a mapping. F of n is equal to an, f of k is equal to a n k. Not A, from natural numbers to B. From natural numbers to B, let us define a mapping by f of k is equal to a n k for all k belongs to n. For k is equal to 1, who is the first member? an1. So n1 is the least positive integer such that an1 belongs to B. He is the first member. Next, who is the second member? F of 2, that is an2. Yes, an2 is the second member in this process we have chosen. an3 is the third member we have chosen. So clearly this mapping is going to be a bijection. This is going to be a bijection. Therefore, n is similar to B. Therefore, cardinality of B is same as cardinality of n. But cardinality of n is alif naught. Therefore, cardinality of B is also alif naught. If cardinality of B is alif naught, certainly B is countable. Countably infinite. Infinite means countable, infinite means countable. Therefore, in this case also B is countable. So in all the three cases we have seen that every subset of a countable set is countable. Every subset of a countable set is countable. This result helps us in concluding one more result. Then what happens to a superset of an uncountable set? Superset of an uncountable set. Superset of an uncountable set. Superset of an uncountable set. Suppose if A is uncountable. Suppose A is uncountable set. A is uncountable set. B is the superset of A. B is the superset of A. Then B is also uncountable. Superset of an uncountable set is also uncountable. Please note this point. Superset of an uncountable set is also uncountable. Suppose A is uncountable, and B is a superset of A. Then we have to show that B is also uncountable. We can prove this by contradiction. For if B is countable, or if B is countable, let us assume B is countable. Suppose B is countable. Then by the above theorem, just we have proved every subset of a countable set is countable. Therefore, if B is countable, A being a subset of B, A must be countable. But A is given as uncountable, which is a contradiction. Not possible. Therefore, every superset of an uncountable set has to be uncountable. Every superset of an uncountable set has to be uncountable. Naturally, a question arises. What happens to a subset of a non-countable set? What happens to be a superset of a countable set? The answer is may or may not be. That means superset of a countable set may or may not be countable. Subset of an uncountable set may or may not be uncountable. Now, for example, just I will prove why it is so. R is uncountable. I will prove it later. N is a subset of R, but N is countable. I will prove this. 0, 1 is uncountable. Closed interval 0, 1 is uncountable. I will prove this. Closed interval 0, 1 is uncountable, which is a subset of real N. This is uncountable. Means subset of an uncountable set may be countable or uncountable. But subset of a countable set is always countable. That's what we proved in the previous theorem. Similarly, superset of an uncountable set is always uncountable. But superset of a countable set may or may not be countable. This is countable. So N is a subset of Z. N is also a subset of R. This is countable. This is superset. This is also superset of N. This is countable, but this is uncountable. This is a countable set. Z is the superset of N. Z is also countable. R is the superset of N, but R is uncountable. So superset of a countable set may or may not be countable. Subset of an uncountable set may or may not be countable. But superset of an uncountable set is always uncountable. Subset of a countable set is always countable. Please note this part. This is another result. One more result I wish to share with you. Every infinite set has a countably infinite subset or denumerable set. Countably infinite subset. Every infinite set has a countably infinite subset, or every infinite set has a denumerable subset. Denumerable subset. So the proof of this result is similar to that of this result, which I proved, that is subset of a countable set is countable. That is the third case. But let me prove it. Proof that A be an infinite set. Let A be an infinite set. Let A be an infinite set. We have to show that A is having a subset which is denumerable or countable infinite. That means every infinite set has at least one denumerable subset. At least one denumerable subset. That means countably infinite subset. Every infinite set must have at least one countably infinite subset. Let A be an infinite set. So let A1 be any member of A. I collect this member in subset. Say I call it as B. Since A is finite, I can find one more member A2. I don't know which is that. Not equal to A1. Not equal to A. I can find one more member A2 belongs to A, but different from A1. Because A is infinite, this is possible. Now I collect this member in subset A1, A2. That is B. I will enlarge this set B1. So please note this, that A be an infinite set. Since A is infinite, there are infinitely many elements are there in A. I can choose any one such member A1. Collect that member in a set B. Since A is infinite, I can find a member A2 other than A1. Choose A2. such that A2 belongs to E, and collect this members A1 and A2. Since B is having two elements, B is not equal to A because A is infinite. Since A is infinite, I can find one more member in A, which is neither equal to A1 nor equal to A2. Choose that member as any such member of A, which is not equal to A1 or not equal to A2, and keep that member or put that member in this collection A1, A2, A3. I have enlarged this. Not equal to A3, not equal to A1, as well as not equal to A2. Continue like this because since A is infinite, this collection is still going to be finite at each and every stage. So therefore, A is infinite. This collection is going to be finite at each and every subsequent stage. So I can find a member of A which is not already present in the existing state. So that choose a new member. I can collect this in the existing collection. I can unlock this. If I continue this process, first I choose A1, next I choose A2, next I choose A3, next I choose A3, A4, likewise. So who is the first member? If I ask, I say A1. Let A1 be any member of A. Choose that one, keep that in a set. Since that is a finite set, but A is infinite, cannot be equal. That means we can have one more element. I can choose one more element in A, which is not already present in the collection in the first stage. And keeping that no element into the existing state set, I can unlock this set, and I can get a new set A1 containing A1 and A2. In the first stage, I collected A1. In the second stage, I collected A2. Since now in the second stage, I have a set containing only two elements A1 and A2, but A is infinite. So therefore, there has to be one element, say A3, which is neither equal to A1 nor equal to A2 in A. Collect that element, which is neither equal to A1 nor equal to A2. Keep that in the set obtained in the second stage. Get a new enlargement. That is a set containing three elements A1, A2, A3. Continue this process. This process of selection is possible because A is infinite. But at each and every stage, we are getting only finite set only. First, we had only one element. Next, in the second stage, we had two elements, three elements, four elements. Continue this process infinitely many times. But if I say in this process, who is your first member? Without any hesitation, I say A1 is my first member. Without any hesitation, I say A2 is the second member. Without any hesitation, I say A3 is the first member. A4 is the third member. Sorry, fourth member, and so on. That means the set which I have collected containing A1, A2, A3, it can be arranged in the members of B can be arranged in the form of a sequence. Therefore, B is countable, but A is an infinite set. B being a subset of A can be arranged members of B in the form of a sequence. Therefore, B is countably infinite. So B is denumerable. Therefore, every infinite set has a countably infinite subset or a denumerable subset. You take any infinite set, dear student. Choose any rule according to any rule. It is a simple logic or a common sense that take any infinite set you want. Choose any rule. According to that rule, you keep on choosing your elements. Keep on choosing your elements. Okay, set of real numbers you take. It is uncountable, infinite. But I can construct a denumerable subset of it. Choose a real number. Choose a real number which is divisible by 2, something like this, or divisible by 2, or which is a natural number. That is the rule. Choose a real number which is a natural number. If I ask, I can choose 1, I can choose 2, I can choose 3, I can choose 4, I can choose 5, I can choose 6, and so on, so on, so on. Now in our collection, we have 1, 2, 3, 4, and so on. So clearly, these numbers can be arranged in the form of a sequence according to some rule. That is natural numbers rule, counting offset rule. Hence, R has a denumerable subset. So any infinite set you take, choose any rule you want. According to the rule, you keep on selecting the members of that infinite set. Whatever the set you have collected, a new set you have obtained by choosing the elements of the infinite set according to certain rule is going to be the countably infinite set. Therefore, every infinite set has a enumerable subset. That's what the meaning of this result. Next, let me move on to an important one more result. Countable union of countable sets is countable. Countable union of countable sets is countable. This is countable. Countable union of countable sets is countable. Here, let AI, I belongs to N, be the countable number of countable sets, countable collection of countable sets, countable collection of countable sets. Please note that here each member is countable. A1 is countable, A2 is countable. A1, who is the first member? A1, because it is a countable collection. This collection itself is countable. This collection is itself is countable, and each and every member of this collection is also countable. That is what is countable collection of countable sets. Here there are two kinds of sets, two sets. One is each member of this collection is a set. It is a collection of sets. It is a set of sets. So yes, it is a collection of sets. That is collection of sets. But each set A1, A2, A3, A4, A5 are countable. The collection of all these sets itself is countable. That's why I can identify who is the first member in this collection, A1. I can identify who is the second member in this collection, A2. Third member is in this collection, A3, and so on. That's why it is a countable collection of countable sets. Countable collection of countable sets. This is going to be countable. How to prove this one? Countable union of countable sets is countable. Since each AI is countable, I can arrange the members of each AI in the form of a sequence. That means members of A1 can be arranged in the form of a sequence, members of A2 can be arranged in the form of a sequence, members of A3 can be arranged in the form of a sequence, members of AN can be arranged in the form of a sequence. So therefore, let us arrange the members of A1 in this fashion. Say A2, A11, A12, A13, A14, and so on. So collect the members of A2 in the A2 is also countable. No? Therefore, members of A2 can also be arranged in the form of a sequence. A21, A22, A23, A24, and so on. Similarly, A3, members of A3 can also be arranged in the form of a sequence because A3 is countable. A31, A32, A33, and so on. Similarly, AN1, AN2, AN3, and so on. Members of AN also can be arranged in the form of a sequence because AN is countable. And continue. The list will not end here because it is a countable collection. It's a denumerable collection or countably infinite collection. Now, what I am going to show, I am going to collect all these elements. This is going to be countable union. Take the union of all these members, all these members, all these members, all these members, all these members. Take the union of members of all these sets. That is going to be the countable union of countable sets. Whether it is going to be countable or not. The answer is yes. This entire collection is also going to be countable. How to prove this? So please observe here. This collection, this entire collection is similar to that of the members of N class N. I can identify A11 with 11. I can identify A12 with 12. I can identify A14 with 14. If I say who is 25, you will say A25. Means I can identify A25 with 25. If I say who is 100 140, you will say A140. A140 means it is a 40th member of A100. 40th member of A100, you will say. Means each and every member of this collection can be identified with 11, 12, 13, 14 like this. So that means this collection is same as N class N. N class N is countable. I have already proved. So therefore, this collection is also countable. But what is this total collection? Countable union of countable sets. Therefore, countable union of countable sets is countable. That means innumerable union of countable sets. Countably infinite union of countable sets is countable. Countably infinite union of that's what innumerable union of countable sets is countable. So, as a particular case, if A is countable and B is countable, A union B is countable. because it is a union of two sets. Finite union is always a countable union. If countable union of countable sets is countable, finite union of countable sets is also countable. Finite union of countable sets is also countable. Therefore, if A, B, C are countable sets, A union, B union, C is also countable because it is a finite union. Countable. Union is also countable because it is a finite union of countable sets. So whenever countable infinite union of countable sets is countable, obviously finite union of countable sets is also countable. So that's one. Because this process is similar to that of listing the elements of n plus n, which I already explained. So n plus n elements can be arranged in the form of a sequence by using rule I explained. So therefore n plus n is countable. Hence, this countable union of countable sets members are in the form are in one-to-one correspondence with the members of n plus n. Means, in the same way, how I listed the members of n cross n in the form of a sequence, I can also list the elements of this union, complete union. Union means this union of I is equal to 1 to infinity. This is what is countable union of countable sets. Union from I is equal to 1 to infinity means this is countable union. Why it is countable union? In this union, I can identify who is the first member. Who is the first member? A1. In this union, I can identify who is the second member. Who is that? A2. That's why it is countable union. Where each member of this member involved in this union is countable. That is what is countable union of countable sets. Countable union of countable sets. So that's what. What about intersection? If A and B are countable, A intersection B is also countable. Because you know that A intersection B is a subset of A as well as subset of B. If A intersection B is a subset of A and subset of B, since A and B are countable, A intersection B is also countable because this is already countable. Subset of a countable set is countable. Therefore, intersection of two sets is also countable. In fact, arbitrary intersection of countable sets is always countable. Arbitrary intersection, it need not be countable intersection. It can countable intersection. It can be any type of intersection. Countable arbitrary intersection of countable sets is also countable. So this is another result. Now I am going to prove an important result or one of the landmark theorem in the study of finite counting of sets. That is, the closed interval 0, 1 is uncountable. Very important. You must follow this carefully. Closed interval 0, 1 in the real line is always uncountable. Closed interval 0, 1 in the real line is always uncountable. How to prove this one? Let us prove it by method of contradiction and Cantor's diagonalization process. Cantor's diagonalization process. Diagonalization process. Cantor's diagonalization process. This is a famous technique used by George Cantor to prove uncountability of closed interval 0. That's what Cantor's diagonalization process. We will come to know what is that. Let us prove first this theorem by method of contradiction. Suppose, let us assume closed interval 0, 1 is countable. Suppose closed interval 0, 1 is countable. Suppose closed interval 0, 1 is countable. Then by definition, members of closed interval 0, 1 can be arranged in the form of a sequence. Then members of 0, 1, closed interval 0, 1 can be listed in the form of a sequence. Can be listed in the form of a sequence. Say x1, x2, x3, x4, x5, and so on, xn, and so on. Since, according to our assumption, closed interval 0, 1 is countable, by definition, members of 0, 1 can be arranged in the form of a sequence. First member is x1, second member is x2, third member. That means each x1, x2, x3, xi belongs to closed interval 0, 1. But every element of 0, 1 has a decimal representation of the form 0 point, A11, A12, A13, A14, and so on, where Aij belongs to the set 0 to 9. Every member of closed interval 0, 1 has a decimal expansion of the form 0 point A11, A12, A13, and so on, where the Aij's are the integers from 0 to 9, as we all know. Therefore, x1 has a decimal representation like this, so I call this as x1. Similarly, x2 has a decimal representation like this, I call this as 0 point A21, A22, A23, A24, and so on, A25, and so on. Similarly, x3 is also such a decimal expansion, that is 0. A3 1, A3 2, A3 3, A3 4, A3 5, and so on. Xn can also be arranged in the form of can be expressed in the form of decimal expansion, that is an1, an2, an3, and so on, an, and so on. Continue this process because each and every xi is a member of closed interval 0. Therefore, they have a decimal expansion like this. Now I am going to construct a new member which is in closed interval 0. I am going to construct a new member which is going to be a member of closed interval 0. But that newly constructed member is not going to be equal to any of the members involved in this list. I'm going to construct a new member and I'm going to show that newly constructed number is a member of closed interval 0, but is not going to be equal to any of these members listed in the sequence. That means what? You have not been successfully able to list all the elements in the form of the sequence because you have constructed a member. You have a new member of closed interval 0, only, but they are not the members of this sequence. This is impossible because had closed interval 0, been countable, all members of closed interval 0, should have been arranged in the form of a sequence. Yes, there is the definite first member, there is a second member, third member, fourth member, fifth member, and so on. So therefore, that means every member of closed interval 0, must be there in this collection. Every member of closed interval 0, must be there in this collection. But I am going to construct a member which is going to be a member of 0, but that is not going to be a member of this collection. That means somewhere your listing of members of 0, in the form of a sequence is not proper. But the thing is, if you arrange them in any fashion in the form of a sequence, I can construct a number of 0, which is not going to be the member of your listing. That means this type of listing is not possible. If this type of listing in the form of a sequence is not possible, that set cannot be countable, hence it is uncountable. That is what is the logic we are going to adapt in proving this. Now let us see how to construct that new member of 0, closed interval 0, which is not a member of this listing of members of 0, in the form of a sequence. Let us define B is equal to 0 point B1, B2, B3, B4, B5, and so on, Bn, and so on, such that Bi is not equal to Aii, such that Bi is not equal to Aii for all I is equal to 1, 2, 3, and so on. That means you have to define B in such a way that B is equal to 0 point B1. B1 should not be equal to A1. B2 should not be equal to A2. B3 should not be equal to A3. Bn should not be equal to An. Here, A11 has 10 choices. Either it could be 0 or 1 or 2 or 3 or 4 or up to 9. Whatever the value A11 is going to assume among 0 to 9, except that value, B1 can take any other value. I can define. Since x1 is the first member of closed interval 0, x1 has a decimal expansion like this. If x1 has a decimal expansion like this, A11 will be equal to exactly one of the member of 0 to 9. A11 must be equal to any one of the whole number between 0 to 9. Whatever A11 is there in x1, I am going to choose B1 different from that A11. Then my B is not equal to x1 because B and x1 are different in their first decimal point. B and x1 are different in their first decimal point. Whatever A11 is there, except that value, I'm going to choose the other number as a B1. That means B1 and x1, A11 are different, means B cannot be equal to x1. Now I choose B2 in such a way that B2 is not equal to A22. A22 is either 0 or 1 or 2 or 3 or up to 9. Whatever, at a time it can take only one value. A22 can take any one of the value from 0 to 9. Whatever A22 value is there, except that value, I am going to choose B2 as other value. then B2 is not equal to A22. If B2 is not equal to A22, if B2 is not equal to A22, then B cannot be equal to X2. Similarly, choose B3 in such a way that B3 is not equal to A33, then B is not equal to X3. Similarly, choose Bn not equal to An, then B is not equal to Xn. So in this way, if we continue, we can come to know that B has a decimal expansion where B also takes the value from 0 to 9. Whole number set only. But B1 not equal to X1, A11, therefore B1 not equal to X1. B not equal to X1. Since B2 is not equal to A22, B is not equal to X2. Similarly, Bn is not equal to Xn, therefore B is not equal to Xn. But B has been expressed in the form of a decimal expansion 0.B1, B2, B3, B4, and so on, where B is belongs to 0 to 9. Apparently, clearly, B has such type of decimal expansion means B belongs to closer to 0. B belongs to closer to 0. But B is not equal to X1. B is not equal to X2. Why B is not equal to X1? Because B1 is not equal to A1. Why B is not equal to X2? Because B2 is not equal to A2. Why B is not equal to Xn? B is not equal to Xn because Bn is not equal to Xn. What? So you define X1 in any fashion. Let X1 be any number in between closed interval 0 and 1, any real number in between 0 to 1. Then A11 is going to choose exactly one whole number from 0 to 1. Now I'm going to define B1 in B in such a way that the first decimal point B1 is not equal to A1. Then B is not equal to X1. Similarly, B is not equal to X2. So we are approaching these diagonal members. We are targeting these diagonal members to prove that B is different from all these Xi's. B is different from all these Xi's, but B belongs to closed interval 0. That's why it is called as diagonalization process. This technique is called as diagonalization process. So 100%, B is a member of closed interval 0, but B is not equal to X1, B is not equal to X2, B is not equal to X3, B is not equal to Xn. That means what? B is not there in your list of collection of members of 0, 1 in the form of a sequence. B is not there in this collection. But if your assumption is correct, all members of closed interval 0, 1 should be written in this form only. That means all members of closed interval 0, 1 should have been one among the members listed on this listed in this collection. But you have constructed a new member B of closed interval 0, 1, which is not a member of your collection. Sir. ಸರಿ ಸರ್ ನೀವು ಹೆಂಗೆ ಹೇಳ್ತೀರಾ ಹಾಗೆ ಇನ್ನೆಷ್ಟೊತ್ತ ಸರ್ ಇನ್ನೊಂದೆಷ್ಟೊತ್ತು ನೀವು ಓಕೆ ಸರ್ ಓಕೆ ತೊಂದರೆ. So this is what is Cantor's diagonalization process. So from this it is clear that our listing is not proper. Means we cannot arrange the members of closed interval 0, 1 in the form of a sequence. That means closed interval, our assumption is wrong. Therefore closed interval 0, 1 is uncountable. Now R is a superset of closed interval 0, 1. R is a superset of closed interval 0, 1. But any superset of an uncountable set is uncountable. Therefore R is also uncountable. What about the set of irrationals? Set of irrationals is also uncountable. Why? Suppose, let us assume that R minus Q is countable. Suppose. But we know that real numbers is the union of Q and R minus Q. Since this is uncountable, Q is countable. If this is countable union countable becomes countable, but R is uncountable. Just I have proved that union of two countable sets is countable. If you assume R minus Q is uncountable, means irrational numbers is countable, then the real numbers would become countable, but that is not. Therefore R minus Q must be uncountable. So Q is countable, R minus Q is uncountable. Why Q is countable? That is important. Q is the set of all rational numbers whose members can be written in the form of P belongs to Z, Q belongs to N, and GCD of P comma Q is equal to 1. Means co-prime integers. Co-prime integers. From Q to Z cross Z means every rational number can be identified as a ordered pair of integers. every rational number p by q can be identified as a ordered pair of two integers p and q, where p is any integer but q is positive natural number. Sorry, means natural number positive integer. Means I can establish an one-to-one correspondence between the members of q and members of z cross z by the mapping f of p by q is equal to p comma q. You can verify this is going to be bijection. If this is a bijection, if this is going to be 1 1, this is going to be 1 1. Of course, bijection agata. It is also going to be bijection. So if it is a bijection, or if it is 1 1, then cardinality of q is less than cardinality of z cross z, sorry, from z cross z to defined like this. F of p comma q is equal to p by q. You can define like this. Instead of z cross z, you can define from z cross z to q. This is going to be 1 1. You can verify. Then, by definition of necessary condition for existence of 1 1 function, if there is a 1 1 function from z cross z to q, then cardinality of z cross z should be less than or equal to cardinality of q. But what is cardinality of q? Well, if not, so cardinality of z cross z is cardinality of beta. So I'm sorry. Let us first one is correct. Q to z cross z. Q to z cross z by f of p by q is equal to pq. It is an ordered pair of integers. Therefore, it is a member of z cross z. This mapping is 1 1. If this mapping is 1 1, by necessary condition for the existence of 1 1 function, cardinality of q is less than or equal to cardinality of z cross z. But I already proved that cardinality of z cross z is alif naught into alif naught, that is alif naught square. That is going to be alif naught. So that means cardinality of q is less than or equal to alif naught. If any set has cardinality less than or equal to alif naught, q should be countable. Q should be countable. Therefore, the set of rational numbers is always countable. But R is the union of rationals as well as irrationals. Therefore, if Q is countable, if R is uncountable, then R minus Q must be uncountable. Otherwise, if this is also countable union countable becomes countable, but R is uncountable. Therefore, set of irrationals must be countable. So this is what is countability basic idea, which I explained. Since most of the students are from BSc and MSc, I explained in detail a bit. But due to the paucity of time, I am forced to close this session. In the days to come, if I get when we get an opportunity, let us discuss about the real number system and properties of real number system. Of course, real number system is going to be an ordered field as well as complete ordered field. Complete ordered field. So just in 1 or 2 minutes, bear with me. Field means R plus dot. Why it is an ordered field? Field means an non-empty set F together with plus and dot. If it is going to be an abelian group with respect to addition, if it is going to be an abelian group with respect to multiplication, but set of non-zero members of F, non-zero members of means F star means F minus 0. Other than 0, if I take the members of F, non-zero members of F, that has to be an abelian group with respect to multiplication. Abelian group with respect to multiplication. And this F plus dot must satisfy distributive law. Distributive law. If these conditions are satisfied, then F plus dot is said to be a field. F plus dot is said to be a field. If F plus dot is a field, and if it satisfies the following properties, then it is going to be called as ordered field. First one is law of trichonomy. Law of trichonomy. Law of trichonomy means for any x belongs to the field F, exactly one of these three should happen. Either x should be 0, or x if I take any x comma y belongs here, either x is equal to y, or x less than y, or x greater than y. Exactly one of these three conditions should happen. Not more than one should happen at a time. Either x is equal to y, if not, or x should be less than y, or if not, x greater than y. Exactly one should happen. That is what is called as law of trichonomy. If you take any two distinct real numbers, any two real numbers, either they must be equal, or one must be greater than the other, or less than the other. Means at a time, only one condition is going to happen. Therefore, set of real numbers is going to satisfy law of trigonometry. And the second one is transitivity, law of transitivity. Law of transitivity. That means if x and y are any two members of the field F, and if x is less than y, and y is less than z, then x should be less than z. X is less than y, and y is less than z, then x should be less than y. Means if x is ordered by y and y is ordered by z, then x should be ordered by z. That's what is that. Transitivity. That is obviously it is going to happen in the case of real line. Next, if x and y are any two members of the field F, such that x is less than y, and C belongs to F, either xc should be less than yc if C is positive, or if C is negative, xc is greater than yc. That is multiplication. This property should hold. And addition, that is if x is less than y, and then for any z belongs to F, x plus z should be less than y plus z. If these conditions are satisfied, then we say, in addition to these laws, if F also satisfies this law of trigonometry, law of transitivity, of that is compatibility with respect to multiplication and addition, then F is going to be called as ordered field. Clearly, real numbers, set of real numbers is going to satisfy all these properties. Hence, R plus dot is going to be ordered field. Similarly, Q plus dot is going to be an ordered field. But C plus dot is not going to be an ordered field, because in C plus dot, law of trigonometry fails. Law of trigonometry fails. Because I, if I take I is a non-zero complex number. That means either I greater than 0 or I less than 0. If I greater than 0, then I into I must be greater than 0. That is minus 1 greater than 0. Wrong. If I is less than 0, then I into I less than 0. That is minus. I into I also should be greater than 0. But minus 1 is greater. I into I square is minus 1 greater than 0, which is also contradiction. So therefore, law of trigonometry fails. Law of trigonometry fails. So because of this fact, C plus dot is not going to be an ordered field. C plus dot is not going to be an ordered field. Why R is complete means if we take any non-empty subset, which is a subset of R, which is bounded above, it is always going to have supreme. So that's why set of real numbers is going to exhibit least upper bound property, similarly greatest lower bound property. That is what is completeness of R. That is, R is a complete ordered field. But Q is not complete ordered field, because in Q we can construct a subset of Q which is bounded above but having no supremum in Q. Having no supremum in Q. For example, set of all x belongs to Q such that x square less than. Set of all x belongs to Q such that x square less than. This is going to be bounded above. Q is an ordered field. It is a subset of Q which is bounded above but having no supremum in Q. Therefore, Q is not going to be complete ordered field, because complete order axiom says that every non-empty bounded above subset of R must have a supremum. Therefore, R is complete ordered field, but Q is not complete ordered field. So in C plus dot is also not complete ordered field, because it itself is not an ordered field. Complete ordered field should be basically an ordered field. That's the reason why C plus dot is also not an ordered complete ordered field, and Q plus dot is also not a complete ordered field. But R plus dot is going to be a complete ordered field, because every non-empty bounded above subset of R is going to be a complete ordered field. The beautiful application of complete ordered field is Archimedean property of real numbers. So due to the paucity of time, I cannot just touch upon these things. Really, for counting of sets, we need some 4 or 5 hours. So if that is the case, I cannot finish off in just 1 hour, half an hour. But I tried my best. I don't know to what extent all of you people have enjoyed. So I'm concluding my session. Thank you. If any doubts, you can ask regarding counting of sets which I have explained.
Thank you, sir.
Thank you.
Questions?
Thank you, sir. for the brief details about real number system and countability. So for the participants, if you have any queries, you are free to ask. Feel free to ask the questions.
If
Okay.
no queries means on 2 occasions there will be no queries.
Yes,
If you have completely understood the concept, then there will be no queries.
Yeah,
If not at all understood anything, then also no queries.
yes, so you don't have any queries means I think you are all got a brief details about the topic. So coming to the last session, that vote of thanks, I would like to thank Dr. Goregoda sir for taking out time from their busy schedule and enlightening us with better knowledge on real number system and countability. So thank you so much, sir. So I would also like to thank our Chief Executive Samash Goyal sir and Honorable Principal Honappa sir for giving permission to organize the session. And I would also like to thank our Honorable Professor and HOD of our department, S. Lingana sir, for leading this session for grand success. And at the last, I thank all the participants, lecturers, students, and other participants for paying your attention and learning. So thank you one and all.
Thank you.
Thank you, sir.
Any other-
So you will get the certificate later on. So feedback form. The feedback form will be sent to the group of webinar 1 and webinar 2. So please fill the feedback form. It's a Google form. And you can left this. And you can left the session now. Thank you.
Oh, yeah.
Start what root connection start what